When a massive cargo vessel takes a heavy roll in rough seas, its survival depends entirely on the predictable behavior of its internal weight. If a ship is loaded with solid cargo, or if its liquid tanks are 100% full, what mariners call pressed up, the internal weight is locked in place. It acts as a single solid mass. Under these conditions, the ship naturally resists rolling over. As the hull tips to one side, the center of buoyancy shifts outward into the water, acting like a lever that pushes back and rights the vessel. But this delicate balance is easily broken by the introduction of a slack tank. A slack tank is any tank inside the ship that is only partially filled, leaving room for the liquid inside to move. When a ship with a slack tank rolls, the liquid shifts. It sloshes and pools heavily on the low side of the hull, shifting the physical center of the liquid's mass. The actual weight of the cargo hasn't increased by a single ounce. But by allowing that liquid to move, the ship is suddenly thrust dangerously close to capsizing. This phenomenon is the free surface effect, a geometric trap that drains the ship's righting energy without adding a single ton of weight. This diagram shows the cross-section of a stable, upright ship. The letter G marks the center of gravity, where all downward weight is concentrated. M is the metacenter, the pivot point for the upward force of buoyancy. When the hull heels, the wedge of fluid inside a slack tank immediately rushes to the low side. The center of mass for that specific puddle of water shifts outward, moving from point lowercase g to G1. Because that water is part of the ship's total mass, its movement physically drags the overall center of gravity off the centerline, shifting it from G to G1. This sketch shows the consequence. The ship's downward weight, W, pulls from the off-center position, G1. Tracing that line straight up to the centerline reveals GV, the virtual center of gravity. Geometrically, the ship behaves as if its mass was hoisted to this higher point. This diagram proves the math of that illusion. The critical righting arm at the bottom, G1Z1, which dictates how hard the ship pushes back against the water, is mathematically identical to the upper arm, GVZV. The vertical distance between G and GV represents a pure, virtual loss of stability. A tiny horizontal slosh of water results in a massive vertical penalty. This formula calculates exactly how much stability you lose, known as the free surface correction. It divides the tank's surface geometry, multiplied by the liquid's density, by the total displacement, or weight, of the ship. The single most dangerous variable here is I, which represents the second moment of area of the tank's surface. To find it, you multiply the tank's length by its breadth cubed and divide by 12. This formula reveals a common, deadly trap. Ask yourself this critical question. Does a tank filled with 5 meters of water pose a worse hazard than a tank with only 10 centimeters? The depth of the liquid is completely absent from the calculation. As long as the liquid is free to slosh the full width of the space, a puddle is just as lethal as a flooded compartment. The real threat is the width of the tank, because the breadth is cubed. If you simply double the width of a tank, you multiply its capsizing force by a factor of 8. To survive this math, shipbuilders install watertight longitudinal bulkheads. Slicing a wide tank directly down the middle cuts the free surface effect to a quarter of its original strength. This is why a few inches of rainwater sloshing across a wide, open vehicle deck capsizes a ship much faster than a half-empty fuel tank. The ultimate test of this geometry happens when a vessel leaves port with marginal initial stability and then begins burning off fuel and fresh water, creating slack tanks. As the tanks empty and slosh, the virtual loss deduction outpaces the ship's initial stability margin. The virtual center of gravity physically rises above the metacenter, resulting in a negative stability value. The moment this happens, the ship can no longer stand upright. In perfectly calm water with zero wind, it automatically falls over to one side. This diagram shows the resting state. The ship will heel until the center of buoyancy pushes far enough outward to perfectly align underneath the shifted gravity. At this exact angle, the righting arm reaches zero and the ship stops rolling. This terrifying resting position is called the angle of lull. While a standard list stems from a simple weight imbalance, An angle of lull represents a total collapse of the vessel's upright physics. When a crew finds their ship resting at an angle of lull, the immediate human instinct is to pump ballast water into the high side of the ship, to weigh it down and pull the deck level. Warning tone. Pumping water to the high side is a critical error. The ship violently rolls through the upright position, gains momentum, and completely capsizes. The objective is to drag the true center of gravity back down below the metacenter, ignoring the immediate instinct to level the ship. Step 1 is to eliminate the existing slosh. Top up any slack tanks until they are completely pressed up, destroying the free surface effect. If you still need to add ballast, you must start by filling small, subdivided tanks on the low side of the vessel. This is an incredibly difficult order to give, because adding weight to the low side of a listing ship will intentionally make the terrifying angle even worse at first. But the physics are ironclad. Water packed tightly into the very bottom of the hull pulls the true center of gravity downward. Once gravity drops below the metacenter, positive stability is restored, and the ship can finally be righted safely. Surviving the free surface effect requires rejecting human instinct in favor of pure geometry. You must calculate the math of the slosh long before you ever touch the pumps.